Shown in the figure below are 2-point charges located along the x-axis. Determine all the following. A, the magnitude and direction of the electric field at the origin, and C, the place on the x-axis at which the field is 0. This problem is, in principle, somewhat simpler than the previous problem where we had 2-point charges. The reason is that both of the 2-point charges, as well as the place where we're trying to do the calculation, the origin, are in a straight line. As a result, we will be able to do a simpler calculation. However, in order to avoid the possibility that students would ever think that electric field was not a vector, but instead a scalar, we are going to do the full calculation all the way out. What I mean by all the way out is as follows. We will consider that at the origin there are 2 reasons why we have an electric field. The first one is the 4 microcoulomb charge, and that will create an electric field E1. And the second reason by which we have an electric field at the origin will be the 2 microcoulomb charge, and that will create an electric field E2. Each one of these fields we will consider the possibility that it has an x component and that it has a y component. Let's begin with the field E1. At the origin, we recognize that since the positive charge is to our left and electric field lines run away from positive charges, the field E1 will be pointed to the right. Because E1 is pointed directly to the right, we recognize that it has 0 y component, and that all of the electric field strength is in the x component. We know that, as always, any electric field will have a magnitude that is equal to K times the charge that generates the field, in this case 4 microcoulombs, divided by the distance squared. Based upon the figure, we can see that the distance is 6, and we need to square that distance. Plugging in the numbers, we find that E1 is 1,000 newtons per coulomb. Looking at the diagram, we recognize something else about E1. E1 is pointed in the positive x direction, so E1 clearly has a positive x component. Next, we'll apply exactly the same considerations to the field due to the negative charge, which we're going to call here E2. Now we recognize that because the second charge is negative, the electric field lines must point towards it. So standing at the origin, the electric field pointed towards the second charge, E2, is also directed to the right. E2 will indeed have 0 y component, and it will have a magnitude given by the same expression as above, except that the 4 microcoulombs has been replaced by 2 microcoulombs, and the 6 meter has been replaced by 1 meter. Plugging in the numbers for this expression, we find a value of 18,000 newtons per coulomb, and we also recognize, looking carefully at the figure, that this electric field is in the plus x direction. Students sometimes have difficulty with this problem because they assume that with a positive charge and a negative charge, there must be something opposite to their electric fields. Well, there is. The electric field points away from the positive toward the negative. And at the origin, away from the positive and towards the negative are the same direction. They're both to the right, and that's a positive x component. So we can simply add these to find E total, which will have a 19,000 newtons per coulomb x component and no y component at all. Since we were asked to find magnitude and direction, we'll do so in a formal manner. And the formal manner says that the magnitude is going to be 19,000 newtons per coulomb, and the direction of the electric field at the origin is 0 degrees, since it's directed straight along the x-axis. Having completed part A, we must now move on to the final part of the problem, and in this case we are asked to find the place on the x-axis at which the field is 0. To accomplish this, we're going to look again at the diagram, only we're going to need to look at it rather carefully. We recognize that at any point between the two charges, away from the positive will be towards the right, and toward the negative charge will also be toward the right, meaning that the electric field contributions from the two of them reinforce one another. There is no way that you could possibly satisfy equal and opposite so as to get an electric field of 0 anywhere between these two charges. That just isn't happening. So let's consider instead the region to the left and the region to the right. On the left, I can label two directions. Away from the positive charge means to the left, toward the negative charge means to the right, and so these will be electric field contributions in opposite directions. Doing the same thing on the right, we'll see that away from the positive charge on the region labeled right is in the plus x direction, and toward the negative charge is in the negative x direction. What that means is that in our attempt to cancel two vectors by asking them to be equal and opposite, we can see that opposite is satisfied to the left of both charges, and opposite is also satisfied to the right of all charges. However, let's think about equal. One of the charges is 4 microcoulombs and the other charge is 2 microcoulombs. In this case, if we were the same distance from both the 4 and the 2, the electric field from the 4 microcoulomb charge would be bigger and they wouldn't be equal and opposite. In order to get the two electric fields to be equal to one another, we need to select, should we be closer to the large charge or closer to the small charge? The answer is, if we want the two electric fields to be equal, we need to be closer to the smaller of the two charges. To the left, you're closest to the 4 microcoulomb charge. To the right, you're closest to the 2 microcoulomb charge, and so for that reason, we recognize that being to the right-hand side of all charges is the only place where we will be able to spot a location at which the electric field will be 0. So let's do our calculation for such a point. And I'm just going to draw a green circle, and the green circle is going to represent some point, and I realize that if I bring this point really, really close to the 2 microcoulomb charge, then the electric field toward this 2 microcoulomb charge is going to be overwhelmingly strong, and I'll have an electric field overall to the left. If I move very, 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 very far away, then effectively I'm almost the same distance from each of the two charges. The 4 overwhelms, and the electric field will be to the right. Somewhere in between exists an x location at which I expect they will cancel. What we're going to do to solve for that location is we are going to write an expression for the electric field at any x which is to the right of the second charge. Then that total electric field, all we have to do is set it equal to the value of 0, and there'll be only one x at which we can satisfy that. Therefore, in this figure, we're going to add one more label, and that is that our point at which we're evaluating the field is going to be a distance x from the origin. We recognize that the 4 microcoulomb charge in the region to the right of all charges is making a contribution in the positive x direction, and so therefore its contribution will be k times 4 microcoulombs over the distance to the charge. Now the distance between the point of calculation and the charge is not x. X is the distance between the origin and the point of calculation. Looking at the diagram, we recognize that the distance from the charge to the point of the calculation is 6 plus x. And of course, for all electric fields, this quantity should be squared. Next, we recognize that to the right of both charges, the electric field contribution from the negative charge is toward that charge, and therefore in the negative x direction. So for that reason, we will have minus k times 2 microcoulombs over some other distance squared. Looking at the ladder diagram, we can see that the distance between the -2 microcoulomb charge and the point P where we're trying to do our calculation could either be written as x minus 1 or as 1 minus x. In order to make the calculations as simple as possible, we are going to select between these two whichever one is a priori positive. Since clearly x must be bigger than 1 in order to be to the right of all charges, we are going to take x minus 1 rather than 1 minus x. This expression tells us the electric field to the right of all charges, and we're going to use this expression to find the place where that quantity zeros. For clarity, we've copied this equation to the bottom of the page, and now we set it equal to 0 in order to find the x at which this is true. Putting these two terms on opposite sides of the equal sign, we see we have a number of useful cancellations. First, the k's go away. Second, the unit microcoulomb that we've been carrying around as a reminder goes away. And finally, we simply have a few numbers. For simplicity, we're going to flip the equation, both left and right of the equal sign, to yield 6 plus x quantity squared over 4 is x minus 1 quantity squared over 2. We can cross multiply and take the square root. Whenever you take the square root, be careful. Mathematicians will always remind you to do plus or minus. We have rigged the x minus 1 to be positive so that we don't have to do that. We can simply take a square root, and after a little bit of algebra, we'll find that x is 6 plus square root of 2 divided by square root of 2 minus 1, which yields 17.9 meters in the positive direction.